This is a video that shows you how to construct an efficiency improvement diagram based on a certain starting point of a solar cell. Now this demo is based on a version of Griddler which is released after February 18th, 2018. And you'll notice in this version there is a built-in efficiency improvement button, which really streamlines a lot of the work involved. So without further ado, let's get started. So let's choose a starting point. Suppose we're working on Perk Cell, and here we have perkexample.met. So let's open it up and see what the parameters are. Let's quickly look at its IV parameters. So we see the starting point is already not too bad. The efficiency is 20.52%. The VOC is decent, 665 mV. JSC is a tad low, 39.66 milliamps per centimeter square. The fill factor definitely can be improved. Right now it's at 77.84%. So let us find out how to use the efficiency improvement button as well as the inbuilt cell parameter database that Griddler provides in order to quickly evaluate what are the rooms for improvement as we implement realistic changes. So to start, we press this efficiency improvement button. And the first thing that Griddler asks us to do is to save the current state of the starting point of the solar cell. So we are free to save it as its current name, overwrite the one that's currently there. And we see that in the background, Griddler is already constructing a script that will execute this sequence of efficiency improvement scenarios and then plot everything in the end. So we don't have to be too mindful about what these details are. But basically what it's doing is it's going to open up and retrieve this starting point of the solar cell, simulate the IV characteristics, and then save these IV characteristics as a baseline case so that it can be compared against the improvements. It will all make sense at the end when we put everything together. Okay, so let's make some room in the window to fit the Griddler main screen as well as this command screen that's logging our activities in the background. So let's together implement a series of improvements. The order of it doesn't really matter and we can be a little bit spontaneous about it. It is important to implement something that's realistic. So based on my take, I see that one area of possible improvement might be the front finger contact resistance. 3 milliohms centimeter square is a little bit high and can be improved definitely. So to help us find realistic value, it's a good idea to open up the cell parameter database, which you can do by pushing this question mark next to the parameter of interest. So here we have this table of all kinds of suggested values. It's good to narrow our search based on the cell type that we're looking for, let's say perk. And still we see a whole range of values reported by different authors. The latest ones that's implemented in the parameter database in April includes some values measured by Alexander Toll and his co-authors at UNSW as they investigate screen print contact resistance on phosphorus emitters that are passivated by aluminum oxide and silicon nitride, and values as low as well below 1 milliohm centimeter square has been reported. That's basically negligible. So why not? We can choose one of these pretty much negligible low contact resistance values and apply it. And maybe we would like to already see how much of an improvement we get just from making this one change. So at this point what we can do is we can go to this command window, and on the bottom here next to comments we can write down what is the particular change we did. Let's call it lower front contact resistance, and we hit enter. And Griddler will automatically log this as a case which we would like to run the IV curve of, after which it will save the IV characteristics under this particular case called lower front contact resistance. Okay, then what is next? Here I noticed that for this particular perk cell, both the base J01, the saturation recombination current density, as well as this effective contact resistance at the rear presented by the rear local openings are not ideal. They are not state-of-the-art numbers. So recall that for perk cell, we can make use of the base transport calculator, in which you can define the geometry of the rear local contacts. Here the opening is stripes. They are 60 micron stripes with a contact pitch of 0.85 mm. At the contact, the recombination is provided by this contact surface recombination velocity of 800 centimeters per second. In the passivated area, it is 20 centimeters per second. So here we can also open up the parameter database And we can see that in 2018, Park and his co-authors have reported values as low as 440 centimeters per second after they have optimized firing using an aluminum silicon alloy paste, and after they have optimized the process to avoid the formation of voids that often degrade the open circuit voltage. So this is a kind of state-of-the-art value that I have seen. So let's also apply this particular number. As for the rear passivation region, the state-of-the-art values haven't changed all that much over the years. So for example, we can apply this value of 10 centimeters per second as reported by Deng and co-authors at Trina in 2017. And that would be a fairly good typical representation of state-of-the-art. Then of course, certainly we can also, change the geometry. Perhaps the contact width can be narrower than 60 micron. 30 or 40 is quite typical. So let's go for 40. Contact pitch, maybe we can tighten up a little bit, make it 0.6, so that the effective rear contact resistance is lowered, while overall we still have a net improvement in the base J01. So let's hit this apply button to apply all these changes. We may close the base transport calculator. And at this point, we would like to have the IV parameters of this step. So let's go to comment again. We call this step optimized rear local contact. We hit enter, and that completes our second improvement. The next improvement perhaps we'd like to be considering is reducing the edge recombination. So right now this recombination is defined by the J01, J02 at the edges of the wafer as very high. So again, if we check out the database, we do see values as low as J02 equals to 1.72 nanoamps per centimeter as reported in 2010 by Daniel Cray in his studies, where he did use some special damage removal treatment for the wafer edge, but nevertheless it's a reference value that we can try to implement and see what is the change. So for this case, let's call this ideally low edge recombination. And finally, let's also make a change to, let's say, the recombination under the front metal contact, which is right now 900 femtoamps per centimeter square. And there are many cell types and layer structures provided in this database, so it is good to narrow it down to phosphorus. And Chen and co-workers at Trina have reported values of 713, so let's try it out. And we call this case lower J01 metal. So let's say right now that we've implemented all the changes we're interested, and we would like to now let Griddler run through each scenario and construct the efficiency improvement diagram. Before we do that, we have to hit this plot button so that we make sure that after running everything, this efficiency improvement diagram will be plotted at the end. So now we're ready to hit the play button. So when we do that, we see that now Griddler will go through the routine. It will first load the starting point, which is the baseline. It simulates the IV characteristics of this baseline. Next, it will implement the improvements one by one, and for each case, simulate the IV characteristics. And then when everything is done, there will be this efficiency improvement diagram. It's showing here the progression of JSC, VOC, fill factor, and efficiency. If we like, we can toggle these graphs on or off. So here, for example, we only show the efficiency. So we see our baseline case starting from around 20.5%. As we implement lower front contact resistance, we gain about 0.1%. Then we optimize the rear local contact, we gain something like 0.15%. And then here we also see that edge recombination is very significant, so that if we can somehow reduce it to the level that one will obtain by special processing, we get more than 0.4% absolute gain. And then finally, lowering J01 metal, that will finally nudge the efficiency just towards 21.3%. If we look at the VOC, although the starting point is pretty high already, we see that, after all the implementations, we do gain more than 5 millivolts, which is quite significant. For JSC, Griddler is only keeping track of the gain and short circuit current density when you change the rear local contact parameters. So in this case, the lower base recombination also leads to improved base collection efficiency, and that gives us a slight gain in JSC. We've seen in the beginning that fill factor was particularly low for this Perk Cell, so we see that our improvements have very significantly raised the fill factor towards 80%. And we understand now that the major limitation in the fill factor was due to this very large edge recombination. So we can actually save this waterfall plot as a JPEG. So that we can pull it up later and look at it. We can actually also refer to this summary.txt for the numbers. So here we see the recorded numbers behind the efficiency improvement diagram. So we have the baseline case, we have the lower front contact resistance, optimized rear local contact, ideally low edge recombination, lower J01 metal. So for each case, IV curve was simulated and the IV characteristics are recorded. So you can always refer back to this file for the numbers. So there you have it. This is a quick little intro to the efficiency improvement diagram and how the entire procedure is streamlined in Griddler 2.5 Pro. And of course, the usage is not limited to Perk Cells. If you're interested to construct similar efficiency improvement scenarios for N-type bifacial or multicrystalline silicon and so on, the cell parameter database is up to date with numbers related to these cell types. And I also hope that will keep you up to date with respect to the state of the art and how it compares to your design and implementation so that you can make an informed decision in your research and experiments.